So are you going to stream it right now or is it already started?
We can start, sir.
So, hello everybody. Welcome to the 17th lecture of Emerging Trends in Biophysics, which has been jointly organized by Homi Bhabha National Institute and Saha Institute of Nuclear Physics, Kolkata. Myself, Professor Padmaja Prasad Mishra. And today I will talk about the second lecture of the sub-series single molecule spectroscopy, where I'll talk about optical tweezer. So we have been discussing about single molecule spectroscopy for last two lectures, and I'm trying to convince you that how the knowledge of single molecule spectroscopy is changing the way we used to visualize or to understand complex phenomena inside nature's nanomachine, that is the any normal cell. So in this way, we'll talk about optical tweezer today, where I'll discuss what exactly optical tweezer is and what are the functions of optical tweezer. Mostly so far we have known that light is used to visualize things, but here I'll discuss how you can use light to help small objects, to hold small objects, and to manipulate small objects even. When I say manipulate, manipulate means moving objects from one place to another place. Well, when we talk about single molecule measurements, the very first question that comes to our mind is why we have to follow processes at single molecular resolution. The obvious answer is because there are many advantages. I should mention here that when we are talking about the cell, the one place where macroscopic view matters is inside the cell. But at the same time, many cellular processes are often carried out at very low concentration and at single molecular level. For example, chromosome replication, segregation, RNA translation, DNA transcription and recombination, and many more. When we carry out any experiment at the ensemble level, we take a whole number of molecules, whole large number of molecules basically. For example, if you take 1 microliter of 1 micromolar solution, there are about 6 into 10 to the power 11 molecules. If you increase the concentration or increase the volume, the number of molecules increases accordingly. So because we take and carry out the experiment taking a huge number of molecules, the signals that we get, the signals that we measure using this ensemble method are truly the unsynchronized average over trillions of molecules. And because it's the unsynchronized average over trillions of molecules, the behavior that we observe, the dynamical behavior that we observe are many times we observe obscure dynamical behavior, and many of the time whatever information we receive are kind of masked. We do not get the right information from those measurements. However, if we do the measurements at single molecular resolution, taking one molecule at a time and we measure it, that allows us to directly measure unique properties, any minute conformational changes inside the system while doing any biological phenomena. We can monitor post-generation, possessive meson, and many more. Basically, when we talk about any cellular processes, we should not forget that the behavior of the cell is mostly guided not only by the chemical changes, only by the chemical signals, but they are also guided by the mechanical properties of the cell and their environment. Cells are able to sense and transduce external mechanical inputs into biochemical and electrical signals, and such mechanotransduction is very, very important in development and homeostasis. Many of the times this mechanotransduction helps us identifying and curing of many diseases also. Though our understanding of the specific mechanism of force sensing, how force is affecting those properties and any cellular properties is very limited. That is because of the development of proper tools with eventual development, with eventual increase in the number of single molecule tools is reducing that gap between, where we understand the minute changes of effect of mechanical forces inside the cell. And one of such development is optical tweezer or optical trapping. We have used light for visualizing things, but this is a tool, as I said, which is used to hold particles, hold objects, or to manipulate, to drag objects from one place to another place. The very first concept of optical tweezer that came to Professor Arthur Erskine, who actually gave this name optical tweezer. And in this particular lecture, we'll learn how optical tweezer works, the principle and physics behind trapping, and the applications of optical tweezer. When we think of tweezers, like I think we are very familiar with this kind of mechanical tweezers. Mechanical tweezers are basically those tools which are used to trap or to hold small particles, which are basically too small to be held by our naked hand. So we can use these mechanical tools, which we popularly called as forceps. And these are nothing but the example of a tweezer. So if the size of the object is visible to our naked human eye, basically a human eye can visualize objects of about 100 micron or bigger than that. But and we can use this mechanical tweezer to hold those size objects. But what if the object size is smaller than 100 micron, or if it is not visualized, if the object is not visualized to our naked eye, we cannot hold the object. And at that time, it is seen that the optical tweezers are helpful for holding those sides and those small objects. And even it is seen that the optical tweezers are able to hold objects which is as small as a atom. The first concept of this optical tweezer came by Professor Arthur Erskine, and he proposed that he can make devices that can hold objects by using light. If there is a refractive index mismatch between the incident radiation and the object, that light is capable of holding that object. And the concept of this holding of this object came from the very basic knowledge that we have learned in intermediate level or undergraduate level, where we have learned that light has a momentum, light carries a momentum, and whenever light interacts with any object, there is a change in this momentum, and this change in momentum is nothing but force. Rate of change of momentum is force, and that force is capable of holding objects. I'll describe those things in details with time. So the first time Professor Arthur Erskine reported this radiative force, or the force exerted by radiation pressure, is in 1970, where he published this paper, this physical review later. So what are the things that can be monitored using this optical tweezer? What can be held with this optical tweezer? We can hold a object which is as big as a cell, or even bigger than the cell, even a glass bead of, or a polystyrene bead of size 1 micrometer, or a small objects like even an atom. And the forces that is required to hold that thing, and forces that is exerted by the light on these objects are about femtonewton or nanonewton range. And basically what is done is a very a high intense laser light. It's tightly focused, and it is believed that at the focus point you can hold the object tightly. So we can pretty much trap dielectric spheres, viruses, bacteria, living cells, organelles, small metals, and even double-strand DNA. This concept of light putting pressure on object that actually came to Professor Arthur Askin after visualizing this Crookes radiometer. What is a Crookes radiometer? In case anyone of you have seen a Crookes radiometer, the Crookes radiometer is almost like a old as electrical ball, which inside is vacuum, and there are very small air inside that, almost vacuum, and there are 4 vanes which are kept on a rotating spindle, and the one side of the vanes are like black coated, and other side of the vanes are white coated. And it is seen that whenever there is any heat energy, a little bit of heat energy or light energy is given to or come close to this Crookes radiometer, this vanes start moving. So whenever any heat energy or radiation is given, this vanes start moving. And the original logic is because whenever we give any radiation, that that increases the heat energy of the atoms which are very close to the black side of the vanes, and that starts giving a energy to per movement of this vanes. But Professor Arthur Askin started thinking that probably it's not only the heat that is creating this motion, probably the energy of that light that we are giving, that is even responsible. Because as I said, this photon, whenever we give any photon, that carries a momentum, and that momentum is probably responsible for rotation of this vanes. So if you talk about a single photon has a weight of 10 to the power minus 27 kilogram, has a momentum of 10 to the power minus 27 kilogram meter per second. And if we talk about this laser pointer, that has about 10 to the power 15 photons per second. So if you calculate the photons, the momentum of this change in momentum of this laser pointer, that comes in the range of newtons, piconewtons mostly, in 10 to the power minus 12 newtons, piconewton. This force, as such, it appears like very less. This force has no effect if we those kind of forces, because we are almost exposed to many kind of radiations once we go out or inside our house as well. But if you are a bacteria or if you have a tiny particle, this radiative energy, as this radiative force, is able to trap you. That's what Professor Arthur Askin explained. So the very first concept, though Professor Arthur Askin reported this concept of optical tweezer light putting pressure on object in 1970, The very first concept of light putting on pressure came in 1669. If you just go to bit history of this optical tweezer, where Johannes Kepler proposed that. So if you see the comments of the tails of the comet, they are always away from the sun. And Professor Johannes Kepler, he suggested in 1619 that the region of the tail of the comets away is because sun is definitely putting some kind of radiation pressure, and because of this sun is putting some kind of radiation pressure that is responsible for keeping the tails away from the sun. This concept, which has been given by Kepler, is verified and by J.C. Maxwell in 1873, almost about 260 years after that, after Johannes Kepler proposed that thing. And J.C. Maxwell proposed a theoretical calculation, and where he calculated the pressure that is exerted by a wave propagating in a medium, and he found that it is numerically equal to the energy content in unit. In another 27 years, it's P.M. Lebedev who carried out some experiment to measure the force exerted by light, which is theoretically calculated by J.C. Maxwell. P.M. Lebedev actually experimentally calculated that thing, and he found out that the pressure which is exerted by the light is twice as great for reflecting surface than the observing surface. Almost 70 years after, Professor Arthur Askin and Professor Stephen Chu together, actually Professor Arthur Askin first proposed that you utilize that concept of light putting pressure on object, and published this physical review letter, where he said that he can capture particles using radiation pressure. Later, Professor Stephen Chu joined him at the Bell's lab, and they published many articles. And I should mention here, this optical tweezer is the only method, only development which got Nobel Prize twice. Once for the application of the optical tweezer, and second for the development of optical tweezer. Professor Stephen Chu got the Nobel in 1997 for pulling and trapping of atoms with laser light, and almost after 20 years of that, Professor Arthur Askin got the Nobel Prize for development of optical tweezer. There is someone whose speaker is not, microphone is on. Can I request if you want to switch off the microphone? Well, let me explain how Professor Arthur Askin carried out this experiment in brief, how he carried out this experiment of trapping particles by radiation pressure. So, Professor Arthur Askin just carried out a simple experiment where he put a lens in front of a laser beam, and there are some particles in front of this lens. Let's say this is the path of the laser beam, and what he saw that whenever he irradiated that laser beam, the particles which are in front of this, like this parallel direction where the laser beam is moving, let's say the laser beam is moving from this direction to this direction, the particles which are in parallel to this laser beam, on the way of this laser beam, they get shifted towards the other side. Let's assume there is a screen there to stop the movement of the particle. So the particles carried out from this side to this side. And eventually, the more number of particles, whatever present here, are been transferred to the opposite sides when he started putting the laser beam. Probably this is how he got the concept that definitely, because the particles are travel from this direction to this direction, definitely it's photon which is responsible, and the momentum that is carried out by the photon is responsible for moving the particle from this side to this side. So, well, what he did is he put another laser beam from this side. So once another laser beam is put, now there are two laser beams, one from this side and one from this side. What he saw that the particles which are eventually accumulated on this side traveled back and stayed at the place where the intensity is more. The intensity is more here because the laser beam is more expanded here and it's more tightly focused here. It's kind of a three-dimensional beam, three-dimensional gradient beam we can call, where the intensity is less here, but the intensity is more here. That means that the information that he observed from here is that when the particles have been kind of trapped at a place where the intensity is more compared to the other places. Well, that actually explains the trapping of or holding of objects using radiation pressure. But what is not explained, so he published this article after trapping these objects in this physical regulator, which was published. Arthur Askin is the only author there. But he has thanked DJ Dinotic for helping him in the experiment. But afterwards, Arthur Askin and James together published about 27 papers between 1971 to 1990, where he explained the other parts of optical tweezers. So, well, this paper, the physical regulator, clearly explained the trapping of particles when there is a gradient, three-dimensional gradient beam. But what was not explained in this paper is what he observed later, that if there are particles which are not in the direction of the propagation of the photon, but in a direction vertical, orthogonal to the propagation of the photon, and what nearby this intense area, if there are particles, they kind of get sucked into the laser beam. So they are not on the propagation of the laser beam, but they kind of sucked into the laser beam also. That is not explained. What are the reasons behind that? So probably there is he thought there is a gradient force which is pulling these objects, which he explained later, and how these objects are being trapped or why these particles are being sucked into the area where the intensity of the light is more can be explained in two reasons. I've divided it into two reasons. One is if the wavelength that we are using is much larger than the diameter of the object, or the second reason I will explain later, if the wavelength is smaller than diameter of the object. Let's consider the first case, first reason, where we consider the wavelength of the light that we are using is much bigger than the object that has been trapped or that has been held by the light. We know that the light has, if it is a polarized light, it has two concepts: the electrical vector, which propagates the electrical component, which propagates perpendicular to the propagation of the light, and the magnetic component, which propagates horizontal to the propagation of lights. And when there is a dielectric particle near that, the electrical field of this radiation that can induce some kind of dipole on the object. How this dipole will induce? Let's say if you, like the previous experiment where I have shown, you put lenses to collimate the laser beam. So if you collimate the laser beam and generate a three-dimensional beam waste where the intensity is less here, the intensity is less here, but at the beam waste, the intensity is more. That is, and you can focus the beam within the diffraction limit, create a diffraction limited spot, the intensity is going to be more here. And when the intensity is more here and you have the object which is going to be trapped is around this more intense spot, the electric field, we can actually consider the electric field that will induce a dipole on the object, which is called as the induced dipole. We can say it as nu. This induced dipole, because of this induced dipole, this object will be attracted towards the higher intense electric. Because the intensity is more here, because of this induced dipole, the object will be attracted towards the more electric, more intense beam. This can be explained considering the coupling between the induced electric dipole moment. As we are discussing the case where the lambda is much larger than the diameter of the object, with a polarizability alpha, the electrical dipole moment can be described as alpha times E. E is the electrical field. The induced dipole moment, the magnitude of the induced dipole moment will be the polarizability times the electrical field. And the energy of this object in this electric field can be explained half of in minus direction, half of induced dipole momentum times the energy, which is half mu E. And if you replace mu with alpha E, we can see it's alpha by 2 E square, and E square is nothing but the intensity of the beam, so it is alpha by 2 I. As the field, the electric field that we see is not homogeneous. This particularly, as I said, it's a gradient electric field which is created by using a high numerical aperture of lens here. So the intensity of the electric field is not homogeneous. The object will experience a force which will drag it towards the more intensity. And how much is the force that is going to be? The force is going to be the change in the gradient versus the energy of the object, which is the energy of the object. We have already figured it out, alpha by 2 times the intensity. So it is minus, there is the gradient field. So the minus of the gradient field times E, which is alpha by 2 times gradient times the intensity. This is the gradient force. So this is the force which will be experienced by the object, which will drag it towards the place where the intensity is more. So this gradient force is definitely attractive force because it will attract the object to go toward the center for a particle which is smaller than the wavelength of the light. But because light is coming and interacting with the object, there is a chance that it will get reflected back also. And because light, I have explained in the initial slide, light has a momentum. If it is reflecting back, there will be transfer of, because if it is reflecting back, the net change in momentum will be, the change in the momentum will be 0. So that change in momentum will be transferred to this object. And according to the conservation of linear moment, whenever there is a change in the momentum, that will be given back by some force, by someone, and that someone here is this object, which will give an equal force on the opposite direction, because change in the momentum is in this direction. The object will give a force which is in the opposite direction. So the object is basically due to the, as I explained, the object is kind of getting attracted towards the center because of the gradient force, which is explained in the previous slide. And now this object is giving a force which is working opposite to the change in the momentum, that is in this direction. So object will give a force towards this direction. And that is nothing but the scattered force. The scattered force can be change in rate of change in the nh by lambda. N is the photon flux per second, and lambda is the wavelength. So the scattering force is rate of change of this photon flux time Planck's constant by lambda, and we can replace this thing with h by nu by c. So the scattering force become n h nu by c times the nm. Nm is the refractive index of the matter. So as d by dt, nh nu is the power of the beam. So we can replace that with the power. So the scattering force become minus power of the beam times the refractive index by c. So this is the power. So scattering force, that means the scattering force mostly depend on two factors. One is the power of the laser beam or the light beam that we are using, and the refractive index of the measure. So this is the force which will be given back by the object because there is a change in the moment. So there are two forces I think I am able to convince you. One is the scattering force, which is moving opposite to the changing direction, I mean in the direction of the propagation of the light, and there is gradient force which is bringing the molecules towards the center. So the scattering force is E square times the energy square times the R6 R to power 6, and the gradient force is the gradient times the scattering force. So for an object to move there, so basically again I'm explaining, if I summarize things, the gradient force is helping the object to go to the center, and the scattering force is asking the object to go down. So if there is a balance between the scattering force and the gradient force, this object will again exactly trapped. So for an object to be trapped at the center, usually the gradient force has to be higher, or there is a balance between the scattering force and the objective force, or scattering force and the gradient force. And to increase the gradient force, one of the way to increase the gradient force is to increase the numerical aperture of the objective. You can use a very high numerical aperture objective of a microscope, so that you can create a very narrow beam width, and that narrow beam width, the gradient, because in a very narrow beam width, the gradient force is higher, that will be able to hold the particle. And once these things are explained, Professor Arthur Erskine explained these things, and this now explains why the particles which are remain away or remain orthogonal to the propagation of the photons also get sculpted into the center of the radiation. And this brings another publication which came in 1987, where he explained basically three things: the reason why these particles which are away from the beam, which are orthogonally present away from the beam but near to the beam width, they get trapped by the center. This is the one thing he explained. Another thing he explained, so the experiment which I explained was done using two beams. So that's why it is called as a dual beam optical tweezer. But in this 87 Nature paper, Arthur Erskine explained that we don't have to use two beams to carry out to hold an object. Even one single beam is sufficient enough to hold an object. I'll explain again in the later slide how one beam is enough to hold an object. So this is the second thing he explained. The first thing he explained that the balancing between the gradient force and the scattering force are responsible for trapping the molecules at the beam waist and even sculpting the molecules towards the center. And you can use single laser beam to trap objects. And another thing he showed there, once you trap the object, okay, he carried out this experiment using a IR laser, a laser 1064 nanometer, because this window of radiation is kind of safe or put less damage to any living objects. So he could successfully hold a yeast cell and observe that the yeast cell remains active once it is trapped, and it does all its function like cell division and everything. You can see initially there are less number of cells, and at this trapped condition, the number of cells are even increasing. So all the normal function of the organ of the cell are remaining intact if even they are trapped by a laser beam. So those are the three findings he explained in this paper. So this comes like the yeast cell. So when he trapped the yeast cell, so initially he was trapping elements or objects which are very smaller. But as the yeast cell, he is able to trap the yeast cell also. So the second design of the explanation comes where why objects are trapped if the size of the objects are bigger than the wavelength of the radiation. So whenever the size of the object is bigger than the wavelength of the radiation, there are three phenomena that can be observed in general. And the good thing is about this design is the entire phenomena can be explained by using ray optics. We don't have to go to much complicated explanation, complicated calculations to observe these things. So we can just use ray optics to explain those things. So in this region, whenever the diameter of the object is greater than the wavelength of the radiation, there are three kind of phenomena we can observe, as I said: reflection, refraction, and scattering. But it is in this regime, it is no longer valid to separate the gradient and the scattering forces because the size is longer here. But trapping can still be understood considering the conservation of linear momentum, which I'll explain. Let's say we have the object here. We have a dielectric particle here whose refractive index is higher than the particles around it. Let's say it's in a solvent. So if you are talking about a dielectric particle, if you are talking about let's say a polystyrene bead or a glass bead, to make the explanation easier, so the refractive index is about of a polystyrene bead is about 1.55, and if water is around, it is about 1.3 or 1.33. So the refractive index is higher for this bead. So whenever there is a input ray comes, so it will interact with the bead, supposed to go like this, but because of the Snell's law, so it will bend. So the refractive index is higher here than the refractive index is lower here, so it will bend towards the normal, and once it bends towards the normal, it will come here, and now before it come out of the surface, so there is again a refractive index mismatch. Now the refractive index of this one is higher than this, so it will bend away from the normal. So a resultant radiation will come like this. The output. If this is the magnitude and the direction of the momentum, as I said, every light carries some momentum. So if this is the direction and magnitude of the momentum vector of the input ray, which is kind of given here, the direction and the momentum, matching the direction and the momentum, and the momentum and direction of the output ray is this, the vector of the momentum on the output ray is there. So you can see that there is a change in the momentum because of this interaction. And whenever there is a change in the momentum, according to Newton's third law, for every action there is a corresponding reaction force, which is equal in magnitude and opposite direction. So if the momentum is in this direction, there must be a force which will work opposite to this direction, according to Newton's law. So there is a force which will work opposite to this direction. So basically the bead is trying, if we carefully look to the entire phenomena, the bead is trying to bend the light to the left, but the light is pushing, because light is putting a force on the bead in this direction. That means light is kind of putting a force. As I said, momentum is directly related to the force exerted. So light is kind of putting a force in this direction. And because light is putting a force in this direction, there is a possibility that the bead, and we can pretty much calculate the force, how much of the force that can be gained by the change in the momentum, which depends upon the intensity flux vector S and the area of the light that is coming. So eventually that gives a pressure which is sufficient enough to put some pressure on the bead. So if that pressure is sufficient to move the bead, so eventually what we see is the bead will move towards the right, because light is actually giving a force. The momentum is changing in this direction. The force is working in this direction. So the bead will move a bit towards the right. Well, so that is the case of refraction, but the same thing will happen in case of reflection and scattering also. So if it is reflection, let's say the beam is coming like this. Let's say we have the object here. One of the beam is coming like this, and it is reflecting back. So there is a change in the momentum, and the change in the momentum works in this direction. And similarly, the momentum change vector works in this direction, the magnitude and the direction. So if the momentum change vector is this direction and this direction, the net change in the momentum vector is in this direction. If you just reserve the x component and y component, and if the net change in the momentum vector is this direction, so it will give a pressure in this direction. So the bead will move towards the right. I hope I'm able to convince you why the change in momentum is shifting the bead towards the opposite direction in the change in the momentum. Let's consider a particular case where instead of using a linear beam, when I said a linear beam, the intensity is almost linear. So let's say instead of using a linear beam, we'll use a gradient beam. Gradient beam has the intensity more as the center, and I have already explained how to create a gradient beam. So we can put a gradient beam by using we can create a gradient beam using a very high numerical aperture objective. So the center of the beam is more intense than the sides, and let's say we focus this beam, whatever is coming, is focus the radiation before the object. So the beam is focused before the objects. Let's consider this case particularly. So let's take one beam in this way. So the beam is coming in this way. It will get bent. It will get bent. I have already explained that thing. So there is a net change in the momentum in this direction. And if we take another beam of this way, the net, so if there is a net change in the momentum in this direction, So the bead will get a pressure which will work in this direction. Similarly, we can reserve this force, which we can reserve this resultant force, which is working on the force. So in the two orthogonal directions, one is in this way, one is in this way. If we talk about the same effect by this ray, so there will be a net change in the momentum which will work in this direction. So there will be a force which will work in this direction as well, same as we observed here, and we can resolve this resultant force in two directions, the y and z direction, which will work again in this direction. So the force, the x component of this beam and the x component of this beam are kind of equal in magnitude, so they will cancel each other. They will cancel each other, and any of this beam who are coming from all these directions, they will keep cancelling each other in the x direction. But if you check about this direction, it will keep increasing up. So there will be a resultant force which will work in this direction. If you are able to, if I am able to convince you, the resultant force will work in this direction now, because there is a resultant force working on that direction. The object will move towards the center of this focus, and it will be trapped at the center. However, whereas the gradient force is working in this direction. However, if we consider the object which is not at the center, so this is the case which we explained, when the object is exactly at the center of the gradient beam, but for some reason, if the object is not at the center of the gradient beam, but it is either of the side of the gradient beam, let's say the intensity is more here and the object is here, so one side of the object will experience an intense beam and another side of the object will experience a less intense beam. So the side of the object which will experience an intense beam, there will be a change in the momentum which will have higher magnitude. But the net change in the momentum from the side where the beam will experience less intensity, the magnitude of the change in the momentum will be less. So the resultant change in the momentum will be in this direction. If you start resolving it the way we have done it here, because the resultant change in the momentum works in this direction, the light will give a force in opposite, so the bead will even move towards the right direction. So here, if the bead is at the center, it will move up, and if the bead is at the right, it will move towards the right side. So if I summarize the entire procedure that I have explained so far, if it is reflection, the bead will move towards the center where the intensity is more. If it is refraction, the same thing will happen. If the object is at the gradient force and the beam is focused before the object will move towards the focus. And if the object is at one side of the gradient force, it will drag towards the object. And if we combine all these things, irrespective of where the beam is, if the gradient force is kind of higher than the other forces, that will be able, and if the net change in momentum is higher, that will be able to bring the particle. If it is not exactly at the focus, it will able to bring the particle to the focus and trap it there, which is called as a stable optical trapping. This is what exactly the optical trapping is, bringing the object towards the center, towards the focus where the light intensity is more, and trap it there. And as I said, optical tweezers are good for manipulating things. So once you are able to hold the object, now you can manipulate it. You can move the bead a bit, or there are two ways to move the beam. One is you keep the laser beam constant, which is actually easier, and somehow make the stage. If you are using a microscope, make the stage move, either using a piezo stage or something. You can move it in XY or Z direction even, or you can steer the laser beam and move the trapping. The latter is a bit complicated. The first part, where you can move the object using the piezoelectric stage or a regular stage, is much easier, comparatively easier. But for if you want to trap the object, the gradient force must be higher than the scattering force. However, if the refractive index of the objective is lesser than the refractive index of the medium, the trapping is going to be metastable. And if you are using a 1 micrometer bead in an IR laser, the trapping force can be roughly said to be 0.03, the refractive index of the object times the power of the laser twice. That eventually indicates that the more the power of the laser, the trapping is trapping force is, or the trapping technically it is called as stiffness of trapping. The stiffness of trapping is higher. But it is not always safe to give a higher intense laser power or a higher laser power to a living object. So that also needs to be chosen carefully. So if we summarize whatever we have seen, to trap a object, we need the gradient force to be higher than the scattering force, and the gradient force can be created by using a high numerical aperture objective. And once the numerical aperture objective is there, and there is an object which is near to the, if even it is not at the center, I have explained that if even the object is not at the center, it is nearby, and some light are passing, this light, if the gradient force is higher, it will trap the object towards the center, and it will trap the object at the center. So the scattering force that works in this direction, propagation of the light, and the gradient force that works towards the center, more intense light, and the gradient force has to be higher. So there are three cases. If the beam is there outside the propagation of the laser beam, but orthogonal of the intense area, then it can be trapped. If it is not at the focus, either. So I have explained a case where the object is below the focus, but whether it is above the focus or below the focus, it will get trapped eventually. So if it is away from the focus, it will be trapped. If it is either off or below the focus, it eventually get trapped. There are some points we should keep in mind while designing the optical tweezer. The small displacements, about 250 nanometer of a spherical particle, the restoring force is directly proportional to the displacement. In that case, the optical tweezer works as a spring, where you can find out the spring constant A into X. The stiffness can be increased either by increasing the gradient in the light intensity, or by reducing the spot size, or by increasing the total flux. So if the total flux, you can keep increasing the total flux of the radiation, because I said the stiffness is directly proportional to the power. So the power is more, the stiffness is going to be higher also. The total distance over which the restoring force acts depends on the size of the bead and the spot of the light. Sometimes, how do you do a manipulation and measurement of stiffness of the trap? I'll not go into details, but one of the common practice that is made while calculating of this spring constant force is by using a detector which is called as a quadruple photodiode. So if you use a quadruple photodiode and you have the particle trapped, and depending upon when you start moving, it will start moving, and the signal can be converted to a digital signal, and the intensity can be measured, and how much the trapping is able to move the object can be back calculated, and from where how much the displacement is there can be calculated. From this force constant, how much the laser is able to manipulate, how much it is able to drag the object can be calculated. Sometimes it is helpful in calibrating the system, also to find out the spring constant of a system. Suppose you have you are working with a sample whose spring constant is not known, and you have a standard whose force or spring constant is known. You can use that thing to calibrate the system. So before building up the optical trap, we should have these components ready: the trapping laser, the beam expansion and steering options. So you need to expand the beam. So one of the easiest way to create a tight gradient spot is you first expand the beam so that you cover the, if this is the objective. So the common practice is you fill up the back focal plane of the cover objective, and then you tightly focused it using that high numerical aperture objectives. You need trapping beads and a sample holder which can hold the sample. Then you need some detectors to monitor the position and to visualize the bit, to monitor the position and to calibrate the position. As I said, you need a QPD, and for visualization of the object, you need a CCD camera, and you need a trap positioning and force controller for that also. The common objectives that are used in optical traps are mostly oil immersion objective. One of the reasons of using oil immersion objective is the good numerical aperture that we get in the oil immersion objective. But there is a problem when we use oil immersion objective, because if you see the focusing of a water immersion objective and oil immersion objective, basically when I'm talking about the focusing, I'm considering the objective is monitoring some liquid sample, some sample which is kept in water, and there is a so if even you put a drop of oil on the objective, still the sample is still water, and there is a refractive index mismatch, which doesn't happen in water immersion objective. So in water immersion objective, there is a single focus point, but in oil immersion objective, because of this refractive index mismatch of the sample and the objective, there are two. The real focus is shifted bit towards the lower range, and the particle is trapped in between the theoretical focal point and the real focal point. This is the typical setup of a optical tweezer. You can see there is a laser beam which is expand using two lenses. These two lenses just work as a beam expander, so that you increase the laser beam as much as possible so that it fills the back focal plane of the objective. So this is a objective. So the laser beam is directed using a some steering optics to the objective, and now this high numerical aperture oil immersion objective creates a very narrow beam waist, a very narrow Gaussian beam waist here, and your sample is here using a XYZ controller piezo stage. So the sample is trapped at this place. So then the light goes there, and the QPD sent to the QPD. so that the positioning detection can happen, and it comes back if you and comes to a camera where you can see the position, you can visualize the position of the bead for carrying out the experiment easily. This is one of the communication by Professor Arthur Askin, where he has shown how he has trapped I'm unable to run this video, but this is where he has seen how he has captured a red broad cell using the optical tweezer. And there are many applications. There are many applications if you just search for the applications of or uses of optical tweezer. The number of publications that are that you can find is exponentially increasing. A lot of people are coming describing the applications of optical tweezer, like optical tweezer and manipulation of nanostructure, dynamic degradation of photothermal heating, single molecular perspective of helicase mechanism and functions, studying single molecule biophysics, and many more applications. So technically, what are the things you can do is select and move a given cell. You can easily trap a cell and move it the way you want. You can remotely apply control forces on living cells, internal parts of the cells even, because I said clearly the optical trap is able to trap even an object which is as small as an atom, which has been published by Professor Steven Chu. So you can use trap very small objects and larger biological molecules without any optical damage if you are not using UV visible radiation and using IR radiation. So you can measure mechanical properties like the electricity of different parts of the cell. You can measure forces generated by single motor molecules in piconewton range. Using optical trapping, you can measure temperature, DNA structure, cell viability, intercellular pH, and many more things. One of the article published very recently is eukaryotic transcription factor, which can track and control their target genes using DNA aligning using optical tweezer. So there is a publication which says that the use of optical tweezer for manipulating micro and nanoparticles by optical nonlinear endoscopy. And there is a recent article which says that this optical tweezer can be used for gene delivery. There are many applications of optical tweezer also. This article describes the RNA reactions one molecule at a time. Like if you use a RNA, which what you can do is you can put 2 bits at 2 ends of the RNA, and there is a ribosome on the RNA, and without even giving ATP, without giving any other components that are required for RNA function and ribosome function, you can just start exerting the force on one side of the RNA, so that you start seeing the RNA is unfolding gradually, and how many nucleotides are unfolding gradually can be seen here. So this says how each step of this says how the RNA is gradually unfolding, and once the RNA is unfolded, the NS3 helicase can go and unwind and ask the ribosome to work on the RNA. There are many pros and cons of optical trap, like any other traps. So The pros are many. We can measure forces and distances, which are well suited for enzyme dynamics and molecular motors. They can work in normal buffer condition, and they are constant. Because radiation damage is a very important factor, and when you use very high power laser beam to trap bigger objects, that eventually ends up having radiation induced damages inside the sample. The instrumental setup and calibration is a bit tricky. Experimental procedure is not that easy. Another classic example of this holiday junction of this optical tweezer is monitoring the branch migration activity of holiday junction, where actually the region of showing this is you can even combine this optical tweezer with single molecule FRET technique. So which once you combine FRET and tweezer, it is called as tweezer, and you can monitor the effect of force and how it is reflected in the FRET. I'll just explain it a bit. The holiday junction, which is usually considered as a good model for showing any kind of nanometer scale changes, because the branches of this, the arms of this holiday junction are dynamic equilibrium with each other and keep changing. So if you just label two different colors at the two branches of this holiday junction, let's say with a donor and a acceptor, once the branches keep away from each other, they will give you a low FRET, and once the branches comes closer to each other, they will give you a high FRET. Usually when there is no magnesium present in the medium, they give a high FRET. When the magnesium is present at some concentration, the branches come closer to each other and they give a low FRET. So this is a very good FRET sensor, and even you can use forces to monitor that thing. So when there is magnesium, increase in magnesium, that starts fluctuating, and you can see that the high FRET state is eventually shifted toward a low FRET state. And once you combine this optical tweezer with the single molecule FRET, you can monitor those branch migration. Instead of giving magnesium or any ion, you can just apply piconewton forces and monitor this branch migration. So you have the donor and acceptor there. You can add another bead towards another end of another arm of the holiday junction and keep applying forces on that. So you use a laser to excite the donor, which is about 532 nanometer if you are using a Psi 3 dye, and you just put a DNA tether, which is about 50 kbps, and use a 1064 nanometer radiation, 1064 laser, so that this doesn't interfere with the FRET phenomena, and you can monitor both. And you can see that when there is no force, the branches keep in dynamic equilibrium between the high FRET and low FRET very frequently. But once you keep increasing the force as small as even 9.9 piconewton or 1.6 piconewton, or keep increasing till 5.2 piconewton, the high FRET state is completely vanished, and the holiday junction mostly like to stay at the low FRET state. This is a very classic example of showing how you can use piconewton range of force to monitor the very small changes inside biological systems. So this comes to an end of the optical tweezer session. So the next lecture, which is on 27th September 2021, that is third lecture in the single molecule spectroscopy series. There we'll discuss about fluorescence correlation spectroscopy.